Okay, so this is lecture 3, and let me check something to see if this is still working. I don't talk into. Okay, yeah, it's working. So now, locally linear systems. Well, before this section, we were dealing with x prime equals like some linear function of x and y, or a linear combination of x and y prime was also a linear combination of x and y. Now, suppose on the right side we have functions of x and y. So it doesn't have to be a linear function. There are two functions of x and y. It can be quadratic, it can be anything. It can be like sine, cosine, e to the power x, anything, any function. So now let's make it more clear. Now, both x and y are functions of time. Remember, I always said and say it again that this x and this y can be considered like x and y of particle, the x coordinate and y coordinate of a particle that is moving in plane. And in time, it's changing. So this is a function of time. So this is the derivative with respect to time. And this is a function which is in terms of x and y, but x and y implicitly are functions of time. Okay, so, but we don't see t here. There is no time here. In fact, we'll see just x prime, y prime, and on the right side we have just x and y, function of x and y. So that's called autonomous. Remember, when the variable, the main variable, which is t in fact, is not present on the right side, then we call that an autonomous system. So the right side depends on just x and y, the things that we are trying to find. Okay, so yeah, I have it on this here. Now let's go back and now critical point. Remember, for linear systems, the critical point, the only critical point was just 0, 0 for an autonomous system, which means the right side there was no forcing function. The forcing, if I have a forcing function here, then the forcing function is a function of time. So that's not autonomous. So we're assuming that there is no forcing function. So the critical point was 0, 0. Well, at critical point we had x prime and y prime 0. So a critical point happened at some time that x prime and y prime was 0. Now, in this situation, in fact, that critical point we will see that this time should be some kind of a, well, let's say in linear systems, that was when we were getting close to this point, the critical point, if it was, say, if the system was stable, then that was when time was like going to infinity, and we never reached that critical point. Why we never reached? Because these two are zeros. So what does this mean? What's going on? What curve passes through a critical point which doesn't have any slope? You see, if this is 0, then when you divide them, you will get 0. So, in fact, we can say that this, we can just say wherever these two are 0. The point was, wherever these two are 0. So, we never reach a critical point, but let's say this goes to 0, say, and y prime goes to 0, say, okay, for some t. No, it depends again. So this means that when this one and this one go to 0. So a critical point happens when this and this are 0. So instead of this thing, we can say critical point is where this thing is 0. So I write xy 0 and gxy 0, and solving this will give me critical points. And I write S in parentheses because we might have more than one, For a linear system, we have just one, that is 0, 0. But for a nonlinear system, which is this, we have functions, nonlinear functions, say on the right side, perhaps, that we might have more than one. We usually have more than one. So that is where, again, where really it's like, you can say that, ask yourself, what solution, what trajectory really passes through this? Nothing. It's like a black hole or something. So, there's really nothing happening there. But everything is getting close. Either it's going out like this or getting close like this. Either way, getting close, or out. That is like a black hole. So it's important to find them. And there's another thing which I showed in that last video that I recorded, which I used mathematical to show you something. When you get closer and closer to that critical point, the curve doesn't reach that critical point. So if this is the critical point, it just goes round and round and round and round. And I showed you, I got closer and closer and closer, as close as 10 to the power negative 11 or something like that. And there was the distance between this curve and the critical point. So it gets closer and closer and closer, never reaches that point. But there's one thing which was interesting, that in a sense it was just repeating itself for a linear system. Now I will show you in another video that I will record for you using mathematical to show you this nonlinear system and phase plane for nonlinear system. That if you have a linear system and if you zoom, for example, for a linear system, let me raise this side. So if a linear system is here. So if your linear system is like this, say, let me just draw some of them. And the scale for you is from, say, -5 to 5, which I, in fact, use -5 and 5 here. If you have linear system, and this is a critical point. If I change it, if I get closer, 5 over 10, 5 over 10, you will see the same thing. It's just amazing. It's like it's repeating itself. Divide, you will see the same thing. Divide, you will see the same thing. It's like zooming in. So you just zoom. It seems that you're just watching at the same thing. The same thing is happening. The same pattern is happening. So getting close to this, when we are dealing with linear system, it's like the same thing. So zoom with, well, don't change this thing. So this should have the same ratio, okay? And then you will see the same thing. Just go in, you will see the same thing. But for nonlinear system, it might look like this, which I will show you in another one, which I will record. So it might be like this. So it might be wiggling, say, so it might be, say, like this. Getting closer. This doesn't have to be 0, 0. That critical point doesn't have to be 0, 0. Let's assume it is 0, 0. Let's assume that this will also give you a 0, 0, which happens a lot. And then when you zoom in, say 100, you will see that these things, these wiggles, they just start going away. So you will see something like this. Closer to what the linear one. And get closer. Get closer, then even the wiggles will basically almost gone. And at some point, if you get closer and closer and closer and closer, you just see the same thing. So get closer and closer and closer, even for a nonlinear system, you will see the same thing. So this is like, it seems that this is acting like a linear system as we get closer and closer to the critical point. And since the critical points are crucial when we analyze some system of equations, because something happens, some instability might happen, right? So the instability of the system happens at critical points, right? So we can study. This one is telling me that if this happens, if when I get closer and closer and closer and closer for a nonlinear system, this is a nonlinear system, it seems that it is acting like a linear system. Therefore, it is telling me that maybe we can analyze this like a linear system. We can analyze stability like a linear system. We can talk about, say, a node and whatever we have. So, spiral or whatever. So, maybe we can analyze this using what we did for a linear system, because it seems to become linear as we get closer and closer and closer to this critical point. So, if this happens, which I will tell you when this happens, then the system that reacts or acts like this is called locally linear. So locally linear means as you get closer and closer, so you zoom closer and closer and closer to a critical point, it seems that the system is acting linear, which means they get closer and nothing changes. It's like a copy of the same thing. That is called a locally linear system, and we can analyze a locally linear system by getting closer and closer to this. Now, why does this happen? Why does this happen? What's going on here that this happens? Well, when we get closer and closer to this, that both x and y, the higher order x and y, in a sense, they just vanish because they are too small. They're small. I will show you why they get small. So, and they just vanish. And they vanish, and the only thing that remains is the linear part of the equation. So, if that nonlinear part vanishes as we get closer and closer to a critical point, then we can just ignore them and treat this thing as a linear system about a critical point. So, let me tell you what I mean by those higher order things. Well, let's go back to Carto and Taylor series. Remember, Taylor series for a nice function which has infinitely many derivatives about point A, say, is fa plus f prime a times x minus a plus 1 over 2 factorial f double prime a x minus a squared plus, and this goes on 1 over n factorial f n a times x minus a to the power n, and dot, dot, dot. So if this is the function, and I have the graph of the function, and this is point A, as I get closer and closer to A, what happens? In either way. As I get closer and closer to A, so as x, this is x, right? So as x gets closer and closer to A from either side, this x minus A becomes small. So x minus a might be 0.00001, say, okay? So that might be, let's say 10 to the power negative 10, 10 to the power negative 20. So this might be very small. then raise it to power 2. So if x minus a is, well, let me write something 10 to the power negative 20, right? So this will be just this one. This will be a 10 to the power negative 40. But this one is still 10 to the power negative 20, this one, right? So this is 1 over 10, or 1 over 1 with 20 zeros. This one is 1 over 1 with 40 zeros. This is very smaller than this, very small. This is small, but that's also small, very small. I mean, compared to this one is basically nothing. So if this one is 0.0, that 1, this is at position 20, that one is 0, blah, 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 position 40, right? So if I just add it to this one happens at position 40. That's you can just ignore it. Just ignore. Now just imagine for n equals like 5, that's way out there somewhere. So you can just ignore it. So as you get closer and closer to A, what remains for you is just this part. Just this part. And you can say that the f of x is this about A. But this is a linear, this is the equation of a line. It's not a linear function, it's an affine function, but it is the equation of a line. That is equation of the line tangent to the curve at A comma FA, right? A comma FA, right? So it is the equation of this tangent line. But you probably don't remember, but that was under linear approximation to a function. And that's an amazing approximation. Okay, now, well, this is not a critical point, that's just any point on this function. So let's see if we have something like this for these two functions of more than one variable. In fact, there is Taylor series for fxy. Well, let me try to remember. So Taylor series for fxy about AB. Okay, so this is about AB. Well, I don't want to refer to Calc 3, but in fact what we are doing is fxy, z equals fxy, in fact. This is a surface in R3. This is a surface in R3. Say, and let me go the other way. So it seems that it is going like this. So you can feel that it is like. Okay, so let's see. So let me. Okay, so this is so this is point AB in XY plane. Point AB in XY plane. Then AB up here gives me a z. So fxy, in fact, when you graph it in R3, you will get a surface. So you will get a surface, and at this point, you can, like this one, this is tangent line, so you have tangent plane. So at this point, you have tangent plane. At this point, okay? And you can approximate the function, this function, about point AB with the tangent plane. Like this one that you can approximate, you can say, instead of dealing with fx, we can deal with this function, which is fa plus f prime a times x minus a, right? Instead of this, which might be a function like a transcendental function e to the power x or something, instead of that, we can deal with this one. And here in dimension 3, we can do the same thing. So instead of this function, I mean the function itself of xy, we can just deal with the tangent plane. The equation of the tangent plane is something like that, except it's an affine function. It has x minus a and y minus b. Okay, so it's in fact similar to that. But let me write down the Taylor series for this one, and you will see what I was talking about. I mean, terms of degree more than 1. I mean, terms of degree more than 1. So this is the Taylor series for AB. If it is f xy equals fab plus del f. Well, del f is this. Del f is fx at AB, fy at AB transpose times x minus a, y minus b, plus 1 over 2 factorial. Then I need like that one, that's f double prime. F double prime is something else. So f double prime, that is fx, fy, it is fxx, fxy, fyy, okay? So I just put them in a matrix, so in fact that is like this, x minus a, y minus b, times a matrix H, then times x minus a again, y minus b. And the plus, the third one, look, over there I have f prime, f double prime, f triple prime. That is the third derivative. What is third derivative here? First derivative. Second derivative will be fxx, fxy, fyy. What is third derivative? Wow, that's fxxx, fxxx, right? Then fxxy, fxyx, f blah 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 blah. So you are dealing with lots of different things. Now imagine if that is the fourth one, then you have all combination of x and y's. Okay, anyway, now let me write h here because the linear part is this. In fact, I'm done. This is the linear part. You can see it's just x minus a, y minus b, which I will write that explicitly. But let's look at that term over there and see what it looks like. So let me erase this. Let me use this thing because it's just making too much. So the h, in fact, is the Hessian, and that h looks like this. That is fxx at AB, fxy. That is a bigger. Yeah, that's capital F. So fxx, fxy, AB, and this is again fxy, assuming that they are the same. Fxy, AB, and fyy, AB. So if I multiply by this and then this, I will get this. So this whole thing will be 1 over 2 factorial. Inside I have fxx. Let me just drop the a and b. Let's write it. Then I have x minus a squared plus 2 fxy, assuming that fxy and fy are the same. AB times x minus a, y minus b, plus fyy times y minus b squared. So when you multiply, you will get this. Okay, that's what I'm talking about. If I am close to point AB, if I'm close enough to point AB, then these terms are compared to this one. And what is this? Let me write this one for you. That is in fact FAB. So that is in fact f AB plus fx AB x minus a plus fy AB times y minus b. So that is the linear term, and that is the quadratic term. If x minus a is 10 to the power minus 20, this is 10 to the power minus 40. If this is also 10 to the power minus 20, this is 10 to the power minus 40, 10 to the power minus 40. Compared to this one, in fact, you're even dividing this by 2. Now, as it goes on, you will get 3 factorial, 4 factorial, n factorial. So the nth one has n factorial. And just imagine that has x minus a to the power n. So that's any combination of x minus n and y minus b to the power n. So that is, compared to this first one, the linear term, they are basically 0. So we can really, when we're getting close to point A and B, we can, instead of dealing with the function fxy, we can deal with the tangent plane. This is the equation of the tangent plane. In fact, those of you who remember from Calc 3, this is the equation of the tangent plane. So it is tangent to the say surface at point AB FAB. So it's tangent, this whatever you call it, Z, is tangent to point AB, comma, FAB. So it's tangent to the graph at this point. Okay, so if when I expand this thing, these derivatives exist at least up to a certain point, and I mean, these derivatives should exist. Fx, Fy should. But the rest of them, who cares? So if only these two exist, then that's it. We have a linear, a nice linear approximation to fxy and gxy about point AB. And instead of dealing with fxy and gxy, we can deal with this. Okay, so let me write this in that format. So first of all, if I have a critical point here, say at point AB, if I have a critical point at point AB, I can move this point to 0, 0. How can I do that? I can move it to point 0, 0, right? I can move it to point 0, 0. So how can I do that? It's just writing x, writing u is x minus a, and v is y minus b, something like that. So if I set u to be x minus a, v to be y minus b, then both u and v are functions of time, and I have u prime is x prime and v prime is y prime. Okay, so this x will be a function, so x will be u plus a and y will be v plus b. Okay, so but when I put it here, I will get functions of u and v, right? So what happens is if point AB is critical point for this function, this thing, then point 0, 0 is critical point when I turn this into u and v. So if I turn this into, with this simple transformation, this becomes u prime is f of u v, say, and v prime is g of u v, and critical point, one of the critical points is AB. Sorry, 0, 0. It will be 0, 0. Okay, so if that happens, and now when I linearize this, f of AB is 0. F of AB is 0, right? So I will get this. When I linearize this thing and ignore the higher order terms, I will get this. U prime is f, well, it's fx, but let's write fu. FU plus FVV, and the V prime will be GUU GVV. Okay, so I can write it in this form. U prime, V prime is this matrix FU, FV, GU, GV, and the U and V. Now these are all at 0, 0. So those are all at 0, 0. Now if the critical point is 0, 0, there is no need to do that, but if not, you can, now what we usually do, we just ignore that AB, because we just find fx and fy, because those constants will just go away. And then at the end, if we want to solve it, we can solve it. In fact, we can say the solution about this point is approximately this. So instead of solving this about AB, we can solve this, which is a linear system. So we solve this linear system, and we can say that the solution to the nonlinear system about point AB, as you get closer and closer to point AB, is the solution to this linear system, which we know how to solve it. We know how to solve a linear system. But as you get further and further, no. As you get further and further, no, the solution is, we don't know what it is, so, but it's not that. But as you get closer and closer, it acts like the linear system, and the solution is basically the solution of the linear system. Okay, so now, all of this that I have written here, I have seen that students can do quite well when it comes to checking stability. In fact, you check stability by checking this, right? So checking stability is checking this matrix. Remember, just the eigenvalues of that matrix can tell you whether it's stable or not, or whatever it is, node or spiral or say saddle or whatever. So basically your job is finding those derivatives, those partial derivatives of those functions. But maybe the hardest part is finding the critical values. Now the critical values, critical points are not values. Critical points are solutions to this system of equations, nonlinear system of equations, algebraic equation. This is not differential, this is an algebraic equation. This is a nonlinear algebraic equation. So you have to find x's and y's, in fact pairs of x's and y's that make both of them 0 at the same time. Not the one x that makes this 0, no. So if an x makes this 0 and a y makes this 0, they are the good pairs, right? So you will see. I will give you enough examples, and there are in fact enough examples in the book. But I will give you enough examples. So what you do is basically find fx and gx, and that is over there, but you have to find critical values before you do anything. Critical points, sorry. Before you do anything. So let's go by an example. Well, let me just pick one that we have here. Well, yeah, I can find one. Come on. I can just one more problem. So this one is x prime, example 1. So I have x prime is 2 plus x times y minus x, and y prime is 4 minus x times y plus x. Okay? But don't worry, you have enough time because your exam is online, so you have enough time to solve this, but be careful. Sometimes students miss some of the zeros, or they find bogus zeros. So be careful. Oh, so if I set this to 0, that is algebra. That is not calc anymore. In fact, so y minus x is 0, then 4 minus x, y plus x is 0. You can guess some of the critical points. Yeah, well, what is the first critical point? My advice is always check 0, 0. Or check 0, 0. Maybe 0, 0 is a critical point. Let's check 0, 0. 0, 0, is it a critical point? Okay. If I put 0 here, that's 2 and 4. 0 here, 0 plus 0, 0. 0 minus 0, 0. Yes. Okay, so at least I have found one. So always check 0, 0. Next. So I have 4 factors here. So either I have this 0, or this 0, this 0, or this 0, this 0, this 0, this 0. Okay, so let's do that, right? If I want both of them to be 0, now the first one is saying 2 plus x is 0 and 4 minus x is 0. Boom, boom. No. Not possible because there's no y here. So first of all, no y, and the first one gives me x minus 2. The second one gives me x4. Oh, come on, we just need one x. So this 0 and this, they cannot be 0 at the same time. So no, this one is not. 2 plus x 0, and this one y plus x 0. Okay, well this can happen. So this gives me x to the minus 2, and if I put this x minus 2 is 0, y is 2. Okay. So y is 2. So 0, 0, and 2 minus 2. Okay, this one and this one, y minus x and 4 minus x. Let me check this. Y minus x and the 4 minus x. So 0 and this one 0. So I will get, well, let's find this x is 4. So y plus 4 is 0. So y is minus 4, right? Is it correct? Minus 4 plus 4. Sorry, that is y minus 1. So this is y plus 4, right? So 4 minus 4 is 0. 4 minus 4 is 0. Right. Okay, so that is x4 and y4. Okay. So 4 comma 4. And at last it is this one and this one. So let's write it. Although I know that will give me 0, 0, but let's do it. 1 minus y minus x, y plus x. If I add them, I will get 2y0, so y is 0, and that gives me x0, which I already found 0, 0. So these are critical points. Okay? So let me write the critical points somewhere so I can erase this thing. Critical points are 0, 0, and then 2 minus 2, and 4 comma 4. I will also do this on mathematical for you, and you will see what it looks like when around or about those 3 critical points. This is like a nice problem. So let's linearize this. Linearize means find, so this is like fxy, and this is gxy. So let's write them fxy. Let's expand this thing so I can find the derivative with respect to x and y. You can find it like this, but I actually prefer to do that. Plus xy minus x squared. So fx xy is derivative with respect to x. I have a minus 2 here, and plus y here, minus 2x, right? With respect to x, this is 0, this is minus 2, this is y, and this is 2x. And fy xy is derivative, so that's 2, and this is 0, so that's plus x, this is 0. So that's fx and fy. Let me write them here. So that matrix will be the matrix fx, fy, gx, gy at critical point is minus 2 plus y minus x squared and 2 plus x. But this is for any point, right? This is for any point. And the other one, I need gx and gy. So let me double check. So there's a minus. That was minus 2 comes from here. Then with respect to x, there's a y remaining and 2x. With respect to y, this is 2 here, 0 and x and 0. Okay, so this is correct. gxy and that is 4y plus 4x minus xy minus x squared. So gx xy will be, this is 0, I have a 4 here, gx minus y minus 2x. With respect to x, this is 0, 4, and this is just minus y, and that's 2x. gy xy is gy, I have a 4 again here, and the minus, oh gee, did I? No, that's correct. So that is minus x here, and that's 0, right? So with respect to y, I have a 4 here, 0, and that is minus x here. So let me 4 minus y minus 2x and 4 minus x. Okay. Since we are just studying stability about critical points, so that's the only thing I will do. Just find just stability about critical points. Then in another video, I will discuss how to solve it and what are the solutions about those critical points. So let's see. Okay, now this guy here. So fx, fy, gx, gy at 0, 0, right? So this is like a function, but it's this kind of function. So let me erase this and so this is in fact 0 will give me 0, 0. There's a minus 2 here. The other one is 2 here, 4 here, and 4 here. Okay? Okay, eigenvalues. I just need eigenvalues, no eigenvectors. So eigenvalues are determinant of minus 2 minus lambda, 2, 4, 4 minus lambda. So I have this time, this will be, let me immediately write with positive lambda plus 2, minus 8. Okay, so that is lambda squared minus 2 lambda minus 8 minus 8. Right? Minus 4 plus 2 is 2, 4 times 2 is minus 8, and there's also another minus 8, so lambda squared minus 2 lambda minus 16 is 0. And well, let's see, let's use that other format, 1 plus minus, this is real, so that's 1 plus 16. So it is 1 plus minus square root of 17. Okay, so for 0, 0, I have, well, let's write this down here. 0, 0, I have lambda is 1 plus minus square root of 17. What is it? 1 plus square root of 17 is positive, 1 minus square root of 17 is negative. So I don't care what that is, but I can just say that 1 minus square root of 17 is less than 0, 1 plus square root of 17. So what situation is this? Lambda 1 less than 0 less than lambda 2. This is a saddle, right? Unstable saddle. Okay? So, let me erase this. Next, what is the other one? 2 minus 2. So 0, 0 is unstable and it's a saddle point, so 2. Now I will plot them for you on Mathematica and you will see. For this one, let's see. Let's see what happens. I have minus 2, y is minus 2, so I have minus 2 again. X squared is minus 4. Is it? Oh, okay. Then 2 minus x, which is 2. No, 2 plus x. That's 2 plus 2. Then 4 minus y is plus 2 minus 2 times 2 is 4. Then 4 minus x is 4 minus 2. So that is in fact minus minus, that's minus 8 here, the other one is 4, that one is 2, and this is 2. Okay? So, minus 8 minus lambda, 4, 2, and 2 minus lambda. Let me double check. I'm in a hurry, but that is okay. So, 2 minus 2, so that's minus 2 plus y minus 2 minus 4. That is minus 8, that's correct. 2 plus 2, that's 4, correct. 4 minus y is plus 2 minus 2x minus 4. So 4, 4 cancel those 2. And 4 minus x, okay. So this is in fact lambda minus 2 times lambda plus 8 minus 8. 4 times 2. So I have lambda squared plus 4 lambda minus 16 minus 8. So I have lambda squared minus plus 4 lambda minus 24. Let me double check. So lambda minus 2 lambda plus 8 minus 8. 6. Sorry. 8 minus 2 is 6. Minus 6 and 8 times 2 is minus 16. So this one will give me, so it is 2 minus 2 will give me lambda, it is minus 3 plus minus square root of 3 squared is 9 minus 24, which is plus 24. And that is 32, right? So it is minus 3 plus minus 32. Minus 3 plus minus 32. Let me double check. That is 3 squared is 9. 33, in fact, right? 33. Okay, so minus 3 minus square root of 33 is less than 0, and the other one is bigger than 0. So what is it against that? Well, so we have two sides there. Okay, so let's check the 4 and 4. quickly. 4, 4. I hope this one is not the saddle, right? I don't think it is, but let's see. So I'm just maybe I have made a mistake. I will check that when I do the mathematical part of it. So -2 plus 4 minus 16, they're both 4. 2 plus 4, 4 minus 4 minus 8, 4 minus 4. Oh, that's good. So, okay. So, this is in fact 16, that is 18, 4 minus 14, is it? 14, right? So, 2 plus 4 is 8. 4 minus 4, that's minus 8 here, and this is 0. Okay. So, minus 14 minus lambda, 8, minus 8, 0 minus lambda. So, lambda, so I have lambda times lambda plus 14, just change the sign of both of them. 8, that is plus, in fact, 64. So I have lambda squared plus 14, lambda plus 64, and I don't need this anymore, so let's write this here. 4, lambda is minus 7 plus minus square root of 49 minus 64. So minus 7 plus minus square root of that is 15, right? Minus 15. I guess so 5, 4, 5, 6, 7. So minus 15, so it's minus 7 plus minus square root of 15i. Complex. Complex with negative real part. Complex with negative real part. This is a negative number. Fantastic. So this is what? Stable spiral. Or asymptotically stable, if you want. Asymptotically stable spiral. Okay? So those two are saddle points, and just this one is spiral. So which point is? So if we get closer and closer to 0.44, where we are good, the other two. So I'm done now, and I will, in fact, do a mathematical part for you, and I will graph this thing. You will see if what happens, and I also will solve it for you about those points. For solving it, you have to do that u and v. So I might solve it here, for example, for 4, 4, and you see how it works when you deal with the u and v, not x and y. Okay, so see you next time.